So first of all, let me hear from group A. Between your two series, AN, which was what we call the alternating harmonic series, minus 1 to the n plus 1 over n, and BN, which was this alternating geometric series, negative 1 to the n over 2 to the n, which ones between AN and BN converge conditionally? Let me start this way, actually. Which ones of them converge at all? The series, ANs and BNs.
Both of them converge with alternating, but AN diverges when you do the absolute value of it.
Okay, so when we throw away the alternating signs, what do these things become? They become the harmonic series. So when I throw away the signs on A sub n, I end up with just 1 over n. And what do we know about the series summation of 1 over n running from 1 to infinity? This should be a Pavlovian response for you. When you see the summation of 1 over n, it's like ringing the bell and the dog is salivating for food at that point, right? Immediately your brain should go, that diverges. That's the harmonic series. And we use the integral test to show that that was divergent. So what do we call a series, an alternating series, which converges, but the sum of its absolute values does not? Conditionally convergent, exactly. So we conclude that this series, negative 1 to the n plus 1 over n, the ANs, are conditionally convergent. By the way, and this is a point that we won't get to appreciate until next week, it turns out that the alternating harmonic series, summation of negative 1 to the n plus 1 over n, actually converges to the value natural log of 2. Why? Wait a few days. And we'll unpack that a little bit. Again, it's rare that we're able to say what a series converges to in this course, but for that one we will be able to show that it converges to ln of 2 next week. All right, so what about the BNs? Its terms are going to 0, and it was alternating, so at least it converges conditionally. What happens to BN when we take the absolute values of the terms? What kind of a series is BN now? Exponential. It's a geometric series. And what's the ratio of that geometric series? A half. So what do we know about the geometric series Bn? It converges. And so Bn is an example of a series which, when it was alternating, it was convergent. And when it was not alternating, it was still convergent. So what kind of convergence does Bn have? Absolute convergence. So there's your two different examples from group A. Starting with the alternating harmonic series, which converged when it was alternating, but when we throw away the negative signs, diverges. So the original series was conditionally convergent. Whereas for the series Bn, the original series, negative 1 to the n over 2 to the n, that converged because its terms were going to 0 and it was alternating. But when we threw away the negative signs, we got the geometric series with a ratio of 1/2, which is still convergent. And so that's an absolutely convergent series. How about group B? In group B, which one of your two series converged conditionally? First one, the Cn series, negative 1 to the n over natural log of n. Because again, the terms were going to 0, and so this alternating series converges by the alternating series test. But when we took the absolute value, so let me ask you, group B, how did you know that the summation of 1 over natural log of n, how do we know whether this series converges or diverges? Look it up on the chart. And which chart is that? Yeah, the thermometer. I mean, we haven't completely proven how the thermometer works at this point, but certainly looking on our order thermometer, that the logarithmic examples, like 1 over natural log of n, those go to 0 at a lower order than the harmonic series 1 over n does. And we know the harmonic series 1 over n diverges, and therefore the logarithmic series 1 over natural log of n diverges. And there are a variety of other ways that we could make that comparison more specific, one of which would be to do a direct comparison. 1 over natural log of n is actually bigger than 1 over n, term by term, for all n greater than or equal to 2. And therefore, since the series summation of 1 over n diverges, so does the series of 1 over ln of n. So there's a direct comparison that would prove that the summation of 1 over natural log of n diverges. So yeah, that makes the Cn series conditionally convergent. And what about the dn's? Negative 1 to the n plus 1 over n to the fourth. Absolutely or conditionally convergent? Group B.
Absolutely.
Absolutely convergent? And how do we know that this series converges absolutely? We know it converges at least conditionally because it's alternating and its terms go to 0. But the question of whether or not it converges absolutely is answered by the convergence or divergence of the series summation 1 over n to the fourth. And how do we know what that series does? Say again? It's a p-series. It's a polynomial series, right? And what is p for this series? And what does that tell us? What does p have to be in order that the polynomial series converge? Greater than 1. And so we get a convergent p-series. Another way of answering that question is to use the integral test. And just to verify that the improper integral of 1 over x to the fourth, x running from, say, 1 to infinity, converges. And it does because the antiderivative of 1 over x to the fourth is x to the negative 3 over negative 3, which, as x goes to infinity, converges to 0. So the antiderivative doesn't blow up, which means the improper integral converges, and therefore the series converges. So I agree, dn is an absolutely convergent series, because it converges whether it's alternating or no. Same thing with the bn's. Whereas the an's and the cn's here were conditionally convergent, because they converged when they were alternating, but when we took away their negative signs and made them positives, they were no longer convergent series. So conditionally convergent series converge only because they're alternating. Absolutely convergent series converge anyway. The distinction between these two is actually deeper than we're giving it credit for in this course, deeper than we can give it credit for in this course. But conditionally convergent series can do really crazy things. One of the things you can do with a conditionally convergent series is you can rearrange the terms. Just change the order in which you're adding the terms to one another. Instead of adding a positive to a negative to a positive to a negative, if you rearrange the order of the terms in a conditionally convergent series, you can actually make it converge to a different value, which is a neat trick. In fact, more than that, there's a theorem that says that if you rearrange the terms in a conditionally convergent series, you can make it converge to any value you want to, which should be even more disconcerting. Absolutely convergent series, when we rearrange the order of their terms, they converge to the same value. But conditionally convergent series, just changing the order in which you add can actually change the value that that series converges to. So a lot of crazy, haywire stuff can go on with a conditionally convergent series that can't happen with an absolutely convergent series.